Okay, so we want to prove that if the limit is x goes to infinity of f is L, and the limit as x goes to infinity of g of x is M, then the limit as x goes to infinity of the sum of f of x plus g of x is L plus M. So in the proof, just like earlier when we proved the sum when x is going to c, not infinity, we need to say what this means. What does it mean that as x gets larger and larger, f of x gets closer to L? What does that mean? So this means if and only if. So given any epsilon greater than 0, we want this. We want f of x minus L to be really small whenever, what do you think that should be? Whenever x is large enough. Given any epsilon greater than 0, there exists an n1 such that this statement is true whenever x is bigger than n1. Okay? Now, what does this mean? The limit as x goes to infinity of g of x equals L means it's the same as, given any epsilon greater than 0, there exists an n2. No reason why it should be the same n1, such that g of x minus L is quite small. It's less than epsilon whenever x is bigger than n2. Okay. Now, when it comes to these n1s and n2s, can I pick a smaller one and it'll still work, or a bigger one? And the answer is a bigger one. Here is n2. Now, x has to be bigger than n2. So whenever x is bigger than n2, this is true. Well, if I pick an even bigger n2, say n, well, x, so it works for, so I'm back to n2, there exists an n2 so that this will be less than epsilon, and n2 has to be, x has to be here, x has to be in here. Well, if you pick a bigger one, let's just call it n, well then x being in here is okay. That is, you can pick bigger n's. Alright, so that's just what I'm going to say. Let's box this in blue. So now, we're going to choose n to equal to the max of n1 and n2. So one of them will stay the same, and one of these two will stay the same, and the other one will get bigger. Alright, so it basically, down here, I am going to write what's in yellow, with one exception. I'm going to say that x just has to be bigger than n. And down, and then underneath that, I'm going to write down what's in blue, with one exception. Instead of x is bigger than n2, I'm just going to say x is bigger than n. To save time, I'm not going to rewrite those two statements. Okay? But in the proof, it should be written, and you better say that n is the max. Okay. So now, what do we know about the sum? What I want to get is that this is true. Well, let's see what this means. We want, let's use a completely different color. We want that the limit as x goes to infinity of f of x plus g of x is equal to L plus M. Well, what does that mean? That means that given any epsilon greater than 0, that we must find an n in the natural numbers such that this minus that is small, less than epsilon, f of x plus g of x minus L plus M, an absolute value is small, is less than epsilon, whenever x is large enough. Oh, let's call that n3. I don't want you to think it's the n from before. This is what we want to show. Okay? And let's see what we have. This here is the same as f of x minus L plus g of x minus M in absolute value. But we know that that's less than f of x minus L in absolute value plus the absolute value of g of x minus M in absolute value. And I'll just make one minor change. Let's say that it's less than epsilon over 2. Okay? So this mess is less than epsilon over 2. This is the first one. Well, let me try to take this is less than epsilon over 2 plus this here is less than epsilon over 2. So the sum is less than epsilon over 2 plus epsilon over 2, which is epsilon. But this is true whenever x is bigger than, well, this was less than epsilon over 2 when epsilon was bigger than n, and this was less than epsilon over 2 when x was bigger than n. So the n3, our n3 should equal the n that we got earlier, which was the max of n1 and n2. Okay? Alright, so let's see what happens. Given n, now this was for any epsilon greater than 0. So what I showed was this, that is this. Well, yeah, I have it. This is less than epsilon whenever x is bigger than n. That's true. That's true. That statement is true. Okay, we proved it below. Okay, so yes, given any epsilon greater than 0, there does exist an n such that f of x plus g of x minus L plus m in absolute value is less than epsilon whenever x is bigger than n. But that's the same as the limit as x approaching infinity of f of x plus g of x being equal to L plus m. Now, if I try to prove the difference, that is, instead of plus, okay, actually here, plus. Now, let's actually prove the other one. The limit as x goes to infinity of f of x minus g of x is equal to L minus m. Now, I claim that this is simple. First of all, so here's the proof. If the limit as x goes to infinity of g of x equal m, then the limit as x goes to infinity of negative g of x is equal to, now we know that constants can come out in front, times the limit as x goes to infinity of g of x. Well, the constant is -1, the limit is m, so yeah, we get negative m. Now, the limit as x goes to infinity of f of x minus g of x, well, we know a rule for plus but not minus. Well, there's a rule in arithmetic that says that you can change that sign from subtraction to addition as long as you change the sign of the second value, which is understood to be positive. In other words, if you have 7 minus 5, this is 7 minus plus 5, because there is no sign by the 5. That is not the sign of the 5. That is a subtraction sign. And you can keep the first number. You can change the operation from subtraction to addition as long as you change the sign of the second number. And that's just what I'm doing. This is f plus negative g of x, which is our function. And we prove that the limit as x goes to infinity of our sum is the limit of the first one, which is L, plus the limit of the second one, which we just computed to be, oh, this should be negative m. We just computed to be negative m, plus -1 times m is not negative L, it's negative m. And this is L minus m. When you have a rule for addition or a rule for subtraction, you can convert it to the rule for addition. Okay, so there's the proof of the sum and difference. Pretty neat.